All right, I just want to go over a couple of things for you guys on Module 13. Remember when we were talking about entropy of a substance? It changes when the substance changes phases. So remember in the solid phase, you have the lowest entropy. The molecules aren't moving around as much, right? They're just able to barely vibrate. And then we go to the liquid phase where the molecules move around more than the solid, right? They're still somewhat close together. And so the entropy of a liquid state's higher than a solid, than a solid state. And then in the gas state, it's the highest entropy. The atoms or molecules move around the most, right? So we go from gas has the highest, liquid has more than solid but less than gas, and solid has the lowest entropy. Okay, so I want to go over on page 473, 474. They just have an example here, and I just wanted to talk about it really quick. So it says, for each reaction, determine the sign of delta S. Okay, so what you need to do is you need to look and see how many things we have in the gas phase. Okay, in doing this. All right. So we have nothing on this side in the gas phase, so there's none. And over here, we have one molecule in the gas phase, okay? So we're going from none in the gas phase to one in the gas phase. So we're going from lower entropy to higher entropy. So there's an entropy increase, so our delta S is positive, okay? And then looking at the next one, we have N2 gas, and then we have 3 H2 gas. So we have 4 molecules on the reactant side in the gas phase. So 4 molecules. And then we have 2 molecules here on the product side. Okay, so in this case, we're going from higher entropy because we have more to lower. So our delta S is going to be negative. Okay. In looking at this one, we have none in the gas phase and we have none over here in the gas phase. But we do have some in the liquid or aqueous phase. And remember, the liquid or aqueous phase has a higher entropy than the solid, right? So we're going from 0 to 11 molecules in the aqueous liquid. So we're going from low to higher. Therefore, our delta S is going to be positive. Okay, so hopefully that's helpful for you guys. I also want to look on page 479. So it says, in the reaction, 2NO gas plus O2 gas, we get 2NO2 gas. Okay, and we found that the delta H, standard conditions, is negative 114.2 kilojoules. If the delta S, standard conditions, is negative 147 joules per Kelvin, what is the delta G at 53.2? So it's supposed to be 532 degrees Celsius, which is also 805 degrees Kelvin. Is it a spontaneous reaction at that temperature? Okay, so we need to do our delta G equals delta H minus T delta S, right? Times delta S. Okay, so our delta S tells us negative 147 joules, but we're looking at kilojoules here, so I'm going to go ahead and convert. So if I put it over 1 and then I times it by 1 kilojoule equals, there are 1,000 joules in 1 kilojoule, so this is going to convert to negative 0.147 kilojoules per Kelvin. All right, great. And then my delta G is going to equal, all right, so negative, right here, my H is negative 114.2 kilojoules minus my temperature, which is going to be 805 Kelvin, times my delta S, which I just calculated, negative 0.147 kilojoules per Kelvin. So my Kelvin will cancel out, and then I will just get, I get 4 kilojoules, which means my delta G is positive, and so it is not spontaneous. Hey guys, since we're on a time crunch and I really want you guys to study for Module 13 test, I'm going to go over the review questions with you. Okay, so these can be found on page 489 of your text. Number 1, in a chemical reaction, where is the potential energy? Where is the kinetic energy? Okay, potential energy is stored in the bonds of the molecules in the reaction. Remember, we talked about this in lecture. While kinetic energy is the heat that's either going to be released or absorbed in the chemical reaction. Okay. Number 2, if a chemical reaction has a positive delta H, will the beaker that contains the reaction feel hot or cold once the reaction is finished? Essentially, they're asking you if this is an endothermic or exothermic reaction, right? All positive delta H's indicate endothermic reactions, right? And remember, endothermic reactions are ones that absorb heat from their surroundings. So therefore, the beaker is going to feel cold. All right. Number 3, why is Hess's law a more exact way of determining delta H than the technique that uses bond energies? It's more exact because it takes into account the phase of each of the substances that are in the reaction. So it's going to be more accurate. Number 4, what is a state function? Give 2 examples. Okay, so a state function is one whose final value is independent of the path, right? So the final destination doesn't depend on the path you took to get there. And what are examples? Enthalpy and Gibbs free energy are 2 examples of state functions. Okay, number 5. Which of the following substances will have a delta H formation at standard conditions of 0? And then we have a few different ones. We have NaOH aqueous, Na plus aqueous, O2 gas, O gas, Cl2 gas, H2 liquid. Okay, so remember, elements that are in their elemental form will have a delta H formation at standard conditions of 0. All right, so NaOH is not an element, so it's not going to. Na plus is not an element either, right? It's an ion. That's why it has that plus charge. O is an element, but the elemental form of oxygen is O2, right? It's a homonuclear diatomic. So the delta H formation at standard conditions for O gas is not 0, but for O2 gas, it will be. And then H2 liquid. So that's not the elemental form of hydrogen, right? So it is a homonuclear diatomic in that it's H2, but H2 is a gas. So, and then I skipped one. Cl2 gas is in its elemental form. Okay, so the only ones that are going to have a delta H formation at standard conditions of 0 in these examples is O2 gas and Cl2 gas. That's it. All right, number 6. Which of the following diagrams indicates an endothermic reaction? What is the delta H of both reactions? So we have diagram 1 and we have diagram 2. Okay, so endothermic reactions have their reactants at a lower energy than the products. Okay, so diagram 1 is an endothermic reaction. So the energy is going to be lower than the products. Here, that's not the case. So diagram 1 is going to be an endothermic reaction. And then it says, what is the delta H of both reactions? Okay, so the delta H of the reaction is just the energy of the products minus the energy of the reactants, right? So for diagram 1, we're going to have about 70 kilojoules, right? And then we're going to subtract, I'm going to call that 18. So it's going to be 70 kilojoules minus 18 kilojoules. So the delta H for diagram 1 is going to be around 52 kilojoules. Okay. There's going to be a little bit of room for error depending on how you read that diagram. And then for diagram 2, I'm going to say this is 60 kilojoules, and then I'm going to subtract. That's about halfway. I'm going to subtract 90 kilojoules. So I'm going to get negative 30 kilojoules for diagram 2. Okay? All right, number 7. Draw an energy diagram for a reaction that has a large activation energy and a delta H of 0. Okay, so if the delta H is 0, the reactant and the products have to have the same potential energy, okay? And then a large activation energy means you need this hump in the diagram to be large, right, at the intermediate state. So if we were to draw, and then this is my energy, and then whatever you're going to put it in, kilojoules, and then my reaction coordinate. Okay, so I basically just need my energy to be something, and then I need to have a large hump, and then I need this to come back down to where it was. Okay, so it's going to look something like that to have a delta H of 0 and a large activation energy. Okay, number 8. If you have two 50.0 kilogram blocks of copper, and one is at a temperature of 50 degrees Celsius, while the other is at a temperature of 25 degrees Celsius, which has more entropy? All right, you guys should know increased temperature means increase in the motion of your molecules or atoms, right? And therefore, that's going to be more disorder, right? So the warmer it is, the higher temperature it is, it's going to have a higher state of entropy. So we have this same amount, same item, same material, copper, and we have 50 degrees Celsius and 25 degrees Celsius. So the one with the more disorder, the higher entropy, is going to be 50 degrees Celsius, right? The warmer block. Okay, number 9. If a chemical reaction is exothermic, but it has a negative delta S, what could you do to the temperature to make it possible to run the reaction? Okay, so you guys know that in order to be a spontaneous reaction, the delta G needs to be negative. Okay, so delta G, it needs to be negative to be spontaneous. All right, and then if we're looking at our formula, delta G equal delta H minus T delta S. Okay, so if a reaction is exothermic, the delta H is going to be negative. Okay, if the delta S is negative, then the T delta S is negative, and the result is a double negative, or the product is added, right? So to ensure that this is going to be negative and the reaction is spontaneous, we're going to need to decrease the T delta S to be lower than the delta H, okay? So in order for this to be negative, we need this to be smaller than this, essentially, right? So if we lower the temperature, that's going to make this smaller. So what could we do to the temperature? Lower the temperature. Okay, essentially that's the answer, looking at your formula. All right, let's flip the page. Oh, that's it. Okay, awesome. Hopefully this has been helpful for you. Let me know if you have any questions before you take your test, and good luck.